Hi, my name is Nikolaus, and in the next 20 minutes I'm going to introduce you to a method for solving integral equations in real time. Our method enables us to simulate light transport with high accuracy for a large variety of use cases. Light transport is simulated by tracing rays from the pixels P of the camera sensor to the light sources L sub E and or vice versa. The most interesting light paths, of course, are those that include interactions with the scene surfaces. Let's have a look at those interactions. There are four different ways to formulate the radiance L sub r reflected in a surface point x. First, we can integrate the incident radiance L sub I over the upper hemisphere, which also needs to incorporate the scattering function f sub r of the surface and the cosine term to account for the change of area of the projected solid angle. Integration happens subsequently on each surface on which the ray is reflected, and numerical evaluation of the resulting nested integral equation is known as forward path tracing. Changing the integration domain to the scene surfaces delta v enables us to connect the point x to any point y on the scene surfaces, which can be used to directly connect to the surface of a light source or to a second path. In the example on the right, our path is connected to a second one originating from a light source. Then, the visibility v of the 2 points x and y must also be considered, and the change of measure introduces an additional term with the cosine of the second angle in the nominator and the distance of the 2 points in the denominator. This term is also known as the geometric term. The third way to formulate the radiance L sub r reflected in the surface point x is to connect with paths that intersect the same surface in the neighborhood of x. Therefore, we first integrate over the local neighborhood, and adding a delta distribution yields equality. Alternatively, we can perform density estimation, replacing the delta distribution with the characteristic function of a ball chi b, and normalize by the area of the circle that is created by the intersection of the ball and the flat surface. Approximating the visibility between x prime and y with 1, because the path originating from y did make it to a point very close to x, we can omit the visibility term, and changing the integration domain from the scene surfaces delta v to the upper hemisphere in the point y approximately cancels out the geometric term. The resulting technique is also known as photon mapping. Finally, we can also rewrite the integration of the incident radiance over the upper hemisphere similarly by again additionally integrating over a local neighborhood of x. In contrast to photon mapping, we use a local average instead of density estimation, and therefore normalize by the integral of all weights in the neighborhood instead of the area of a circle. In the limit, that is for a radius going to 0, this formulation is again equivalent, but for any non-zero radius, this method trades a certain bias for a reduction of variance. This technique that we named path space filtering can be seen as a dual to photon mapping and is the core of the method that I am going to present today. Path space filtering itself has already been presented here at MCQMC 4 years ago, and my talk today will focus on a modification and several implementation details that make the method suitable for real-time applications. But before we talk about these details, let me first show you some motivation to illustrate why we want to trade the bias of such a local average for the reduction of variance. This is an image rendered with forward path tracing. That means we start a number of rays per pixel on the camera sensor, trace them through the scene, and add their contributions once they hit a light source. Since the integrals are evaluated numerically, using only very few samples, like one sample per pixel on the left, results in a lot of noise. While image quality of course increases with the number of samples, 16 samples in the middle is already quite okay in the scene, and after 1024 samples on the right, the image has visually converged. Unfortunately, the time budget for real-time applications currently only allows for one or a few samples per pixel at most, and therefore we need very powerful variance reduction techniques, like path space filtering. Before we get to the modifications of the algorithm, let's first walk through the original method step by step. First, like usual, paths are traced from the sensor to the light sources, and scattering is simulated on the surfaces, and optionally also in volume for phenomena like fog, haze, or clouds. Historically, splitting rays by sampling more than just one direction of the hemisphere has been used to reduce variance. Unfortunately, the computational cost for this variance reduction technique is high, since the number of rays grows exponentially with the path length. Path-based filtering overcomes this limitation elegantly by reusing paths instead of creating additional ones. Given a set of paths, the radiance in points of interaction, also called vertices, is stored. This is in contrast to pure path tracing, where only radiance in the points on the sensor is stored. It is important to note that the radiance in these points is usually either available for free or at a very low additional cost, since it is used in the path tracing process anyway. Then, at each point of interaction, the average of the radiance in other vertices with a similar descriptor is calculated and used. This descriptor includes the position and also a few additional attributes that help taming the bias. I'll get into the details of the descriptors in a few moments. One interesting observation is that this filtering technique can also be seen as an efficient approximation of splitting, where the origin of the scattered ray is slightly shifted on the surface. Looking closely at the algorithm reveals its main bottleneck, the calculation of the averages. In order to maximize variance reduction, we want to include many contributions that are classified as close by in our average. So for each point of intersection, we need to loop over all vertices we stored, check the characteristic function chi_b, and potentially add their contributions cs I plus j multiplied with a weight based on a similarity measure to a sum. A second sum in the denominator sums up all the weights of vertices we included in order to calculate the weighted average in the end. While we can efficiently cull vertices that are definitely outside our search radius, here shown as areas hatched in green, we still need to iterate over all of them, and, even worse, every vertex needs to do this individually. The main idea of our modification is to reformulate our criterion that determines which vertices are close by, so that a collaboration is possible. Let's see how this works in a simplified filtering example. Here, for the sake of simplicity, we are going to filter a simple gradient in 2 dimensions only. This is the result of a typical dithering application, in which samples are either black or white. For each vertex, which in this example is just a pixel of the image, we can calculate a local average. The result is an image filtered with radial blur. The idea that enables collaboration now is to replace the distance in the criterion for close by with a binary function, which is 1 if the quantized descriptor of 2 positions is equal, and 0 otherwise. In this simple example, the descriptor is just the position, and as a result, we get 1 average per cell instead of 1 average per pixel. Since the grid-like structure imposed by quantization is visually unpleasant, artifacts can be hidden by jittering the descriptor both when storing a value and when looking up the averages. The resulting uniform noise can later be filtered with a much simpler filter if desired. Jittering can also be seen as a stochastic evaluation of interpolation. Leaving this simple example behind, in which the descriptor was only defined by the 2-dimensional position of the vertex, let's now have a look at descriptors suitable for path tracing in 3 dimensions. First and foremost, the descriptor includes the world space position of the vertex, so that only vertices in a spatial neighborhood are considered. In addition, it can, for example, include the normal n to avoid smearing across edges, the incident angle omega to allow for filtering of non-diffuse surfaces, and the selected layer of multilayer materials. Given a set of descriptors of vertices, we then use a hash as a mapping from the descriptors to memory locations in a hash table. Since this is a direct mapping, no pre-processing or hierarchical data structures are required, and all access can be performed in constant time. Hash functions may map different descriptors to the same memory location. This is called a collision and requires additional efforts. Therefore, for a fast implementation, we trade a larger hash table size for faster access, because larger table sizes result in less collisions. Also, we only use very simple and very fast hash functions and only use linear probing for collision resolution. Linear probing simply checks the next cell until either a cell with the same descriptor or an empty cell has been found. Finally, as our descriptors can be very long, we use a second, different hash of the descriptor for comparison. This hash is much shorter than the descriptor. Hashing is key to sparse function approximations with high dimensional descriptors, because in this case, collisions are very unlikely. Since the lookup for the average for each vertex can now be done in constant time, the complexity of this variant now grows linearly with the number of rays instead of quadratically. Let's go through the mapping from a descriptor to a memory location in the hash table step by step. First, a hash function is applied to the position x and potentially also to other properties of the vertex. This hash is then mapped into the table by wrapping it with a modulo operator. Then a second different hash is calculated, which we will later use instead of the descriptor. The method can easily be extended to support level of detail, for example based on the distance of the vertex to the position of the camera. By scaling the position with this level of detail, the quantization resolution gets larger and larger with increasing distance to the camera. Finally, we can jitter the point before quantization by first determining the initial level of detail and shifting proportional to the size of the quantized cell at the original position of the vertex. Since the shifted point may then end up closer or further away from the camera, the level of detail must be recalculated. This is an example of the procedure in which the first steps that perform jittering are omitted. Again, like in the two-dimensional example, you can see the grid structure imposed by quantization. Adding back the jittering steps hides these discretization artifacts in uniform noise. In this example, filtering was performed in the first ray surface intersection, which makes the grid structure visible. The main power of the method that differentiates it from other filtering techniques that, for example, filter in image space, is that filtering is now possible in every ray surface interaction along the path. In fact, in many practical cases, at least additionally filtering in later positions along the path is even more important for variance reduction. Also, since already the first ray surface interaction integrates radiance, discretization artifacts often disappear even without jittering when filtering in these later positions. This is an example where we filtered in the second ray surface intersection. The input to the method is shown on the left, and the filtered result is on the right. This part of the scene is mostly indirectly illuminated, and since finding indirect light paths is often much more challenging, the result of variance reduction by filtering is even more pronounced. In interactive simulations, variance can be further reduced by also filtering in the time domain. There are two different concepts that unfortunately often are confused: temporal filtering and temporal integration. In the vast majority of graphical applications, exponential moving averages are used for temporal filtering. Such an exponential moving average is a one-tap low-pass filter that updates the filtered value f tilde by scaling it by a factor 1 minus alpha and adding the current value scaled by alpha. While it is often also abused for temporal integration, it is crucial to note that such an exponential moving average will not converge, but actually lag and blur over time. In the example image, a light is shining down on the street and is moving relatively fast. And the shadow that you can see on the street in the image is actually supposed to be sharp. Temporal integration, on the other hand, which can also be calculated as a running average by using 1 divided by n instead of a constant alpha, does converge over time, but makes the scene adapt less and less to changes in the illumination, since the weight of each new value gets smaller and smaller over time. The image shows that we now actually calculate the average illumination over time, which is also not desired. Since both moving averages only differ in the way alpha is calculated, we can also create a hybrid that gets the best of both worlds. This is the result of filtering with this hybrid moving average, in which alpha is set to 1 divided by n if no temporal changes are detected, and otherwise to a value between 1 divided by n and 1, depending on the amount of change. Note how the shadow is crisp. For illustrative purposes, we disable jittering for the image. Changes can, for example, be very elegantly detected with temporal gradients, which fit very nicely into the final filtering algorithm, which then also gives us filtering of the sampled gradients for free. Finally, here is an image of an application using the method. The input of the method, path traced global illumination with 1 sample per pixel, is shown on the left, and a reference is on the right. The filtered result of the inputs is in the middle. While the visual fidelity does not exactly match the reference, it gets very close, and filtering only adds an overhead of 1 millisecond for images in HD resolution on a modern GPU. To conclude, let's recap what we've seen in the last few minutes. The method I presented solves integral equations faster by using an efficient filtering method for variance reduction. The complexity of this method is linear in the number of paths instead of quadratic, employs hashing for sparse function approximation, and hides discretization artifacts by jittering. It can be used for much more than just for light transport simulation. For example, we also successfully accelerated reinforcement learning with it, and we would be very curious in other applications that you may come up with. There's a preprint already available on arXiv, and the method has already been used in several products and in follow-up research. And with that, I would like to thank you for your attention, and I'm looking forward to hopefully being able to meet you in person at the next MCQMC conference.